All right, we're going to start looking at some logs and exponential functions. So we're going to apply those same kind of transformations that we've been looking at with your other functions. So the difference here is that your function now is f of x equals a to the x power. So our variable, our x, is in the exponent position. It will always have, really, you usually see this more as a b, a base b that is greater than 0 and cannot equal 1. All right. And so you can tell when your growth versus decay based on the value of that b. And so if your function has a base value where b is between 0 and 1, so a fraction value, then it's going to be exponential decay. And so these here would be exponential decay. Where if that value is greater than 1, so a whole number value or even a mixed number, but a number bigger than 1, then you're going to have exponential growth. And so again, we're looking at your base value here, what is being raised to the power. Now, your b value is not going to be negative. That's why it always needs to be greater than 0, because otherwise, if you think about your rules of exponents, that would bounce back and forth between positive and negative values depending on whether your exponent is even or odd. For 5 here, e is a number, much like pi. E is equal to 2.718, and so this function here will represent growth. All right, because it's greater than 1. So properties of exponential functions. Again, the exponential function f of x equals b to the x for b greater than 0, and where b cannot equal 1 has the following properties. Your domain is always all real numbers. The range will be from 0 to infinity unless there is a transformation. So this is your parent function. The function f is increasing for b greater than 1 and decreasing if it is between 1 and 0. So again, decay versus growth. And the graph has an x-axis as a horizontal asymptote. So your x-axis 0 is your horizontal asymptote. All right. So we look at transformations in the same way we always have, right? This will be a vertical shift. You'll have your horizontal shift. You'll have your multiplier, your scalar that will reflect it and possibly make it go up a little bit faster or stretch it or shrink it or whatever. And so here, if you're looking at f of x equals 2 to the x plus 1, make sure when you write this in your graphic calculator that the x plus 1, the whole thing is in parentheses. This is going to move left 1. So opposite when it's with that x, just like it has always been. So if you have a function that shifted left 1, so you can get your point from a graphing calculator, but every graph will go through 0, 1. And so if this is going to move left 1, it's going to go through 0, 2 instead, because this point's going to move and then that point will move. So I would just get your graphs, your points off of your graphing calculator. And so you can see here your domain is still all real numbers. Your range, though, is going to go from 0 to infinity using parentheses because it's never going to hit 0 because we have an asymptote at y equals 0. All right, again, unless there's a shift. So like with this one, we're going right 3 and up 1. And so because of that vertical shift, it changes where our asymptote is located. And so on your graph, you're going to have a horizontal asymptote at y equals 1 because we're going to shift that whole thing up 1. So again, we're crossing here. oh no, I forgot about the right shift. So the point that would cross here goes right 1, 2, 3, and then up 1. And so it's actually located here. There's another point just above that. And then again, you can get some points from your table or plug in values here. So like maybe plug in 3 because that makes that 0. And you can see 2 to 0 is 1 plus 1 is 2. So that's where we get this point here. So this line goes this way. Your domain is still all real numbers. Your range is still 0, or excuse me, this time it's 1 to infinity because we shifted up 1. Your asymptote is y equals 1. This last one has a down shift of 2, but it's also flipped over the x. All right, and so your asymptote this time, because we're going down 2, is at y equals -2. This is going to change your range value because it's going to flip it upside down. And so we have this horizontal asymptote here at -2, and instead of going up from here, we're going to go upside down from here. And so we're crossing at -3, 0, because that point here has gone down to, and then we're flipping over from there. So again, pull, let's see, 1 is -4. I'm just plugging those points in my head. Pull some points off your graphing calculator, and it would look something like this. So our domain remains the same. Our domain for all of these should be all real numbers, or negative infinity, positive infinity. The range for this one is negative infinity to -2, excuse me. And your asymptote for this one is y equals -2. Notice I'm writing all of those as equations there. So you also have your formulas that apply this, and this is actually pretty applicable to real life, where you have annually, and your N will be 1, semi-annually is twice a year, monthly is 12 times a year, quarterly would be 4 times a year, and daily is 365 times a year. So in your formula, you have your P is your principal or the amount that you start with, T is your time in years, your annual interest rate as a decimal is your R in both of these equations. And so we can do it compounded a certain number of times per year, or if it's continuously compounded, we're actually going to use your E value, which is a button on your calculator. So for problems like that, you're really just plugging into the formula, show me where you plug in, and then the rest from there is calculator work. Okay. All right, so moving into the inverse. The inverse of an exponent is a log. And so we can recall that the exponentials we were just looking at are what we call one-to-one functions because they pass the HLT and because they have an inverse. Oh no, sorry. Exponentials are one-to-one because they pass the HLT. So exponentials have an inverse, sorry. All right, so to begin, we look at the function of x equals 2 to the x power, and we want to find its inverse. All right, so just to kind of show you where this comes from. Remember, to find an inverse, we flip the x and the y, and then we have to solve for y. Well, the problem with this is we can't get y out of the exponent position. And so the solution to that is to change it to a log. And so we rewrite this as log base 2 of x is equal to y. A log will always equal your exponent. And so in inverse function form, f to the -1 of x equals log base 2 of x. All right, so your definition of a log function means that if you have y equals log base a of x, we can go back and forth between exponential and log form, this is the same as a to the y is equal to x. All right, so being able to convert back and forth will really benefit you here with these. Logs are really just rewritten exponents. All right, so the inverse of an exponential function is a logarithmic function, and vice versa. All right, so things that you'll need to know. There is a log button on your calculator. This is what's referred to as a common log. It has a base of 10, and so if you see log x, it just means log base 10 of x, but we don't write that 10 there. We don't write it like this. All right. For a natural log, that's also a button on your calculator. You're not going to write it as log base e of x. You're going to write it as the natural log of x. Okay, so this is what it means. This is how we notate it. Being able to switch from one form to the other. All right, so if we want to express this equation in exponential form, we're just going to take our base. The base of the log is the base of the exponent. A log is equal to the exponent, and so we raise it to that power, and then it's equal to whatever we were taking the log of. All right, then the opposite way works as well. Whatever the base of the exponent is the base of the log. All right, we're taking the log of whatever's on the equal sign, and then it's equal to your power. Now this is going to be rewritten as just log of x equals 5 because we don't put a base 10 on our log, and so that would be your final simplified form. All right. All right, so go ahead and try practicing going back and forth between those. Okay, and so you can see I just moved the 10 to the base, the 3 to the power, the 1,000 to the other side of the equal sign. 10 cubed is in fact 1,000. 2 to the fourth, so base of 2, it will equal 4 of 16. And then 3 to the negative second is 1/9. Okay, so you're just moving it around. Okay, same thing here. Go ahead and try moving these. It doesn't matter if you have something like 1/2 to the third power equals x. Whatever is in that base goes to the base of your exponent. Remember, if there is no base showing, that's a 10. If it's a natural log, then it's an e. So this would be e to the 4 minus y equals 7. Okay, try those other ones on your own and we'll fill the rest in class. Now, properties of logs, make sure you pay special attention to these. Now, remember, a log is an exponent. And so when we're looking at these certain properties of logs, we want to just kind of consider what this means. This would mean a to what power is equal to 1, right? And so we want to know what goes here. And that would be 0. Anything to the 0 power equals 1. Same thing here. This means a to what power would equal a. And so if the base and what you're taking the log of match, then it's always 1 as your answer. This here means a to what power is equal to a to the x power. Well, if my base is matched, then my exponents must match too. Think like 2 to the third must equal 2 to the third as well. And so this is just going to equal x. That's what would go in that blank there. And then here we have a to what power would equal log base a of x. All right, and so remember, a log is an exponent. These are just going to cancel each other out. It's easier just to do it here. If this matches this, then these cancel out, and it's always just x. All right, so those are the properties for now. We'll go over some more laws of logs in the next lesson. So go ahead and try to practice using some of these properties here. So if it's log of 1, no matter what the base is, this will always equal 0. All right. If these two match, then it's always equal to your exponent. All right. If these two match, then it's always equal to what's behind the log. All right. Keep in mind, if there's no base showing, then it is a 10. All right, log base 12 of 12, those match, so that is just 1. 12 to the first power equals 12. The natural log is a base of e, so those match, and I get 150. All right, ones like this where you have log base 5 of 1 over 25. Again, think about what you can change this to or what you can raise this to get it to be this log. All right, this is just rewritten. We can rewrite this as log base 5 of 5 to the negative 2. And so that would equal negative 2. So try to get your base and your number to match here. Same thing here on 16, log base 3 of 3 to the 4th. Try to get those to match because now that's equal to 4. All right, so if possible, I'm going to do that. This one would just equal 5. This is log base 10. Well, I can rewrite 10,000 as 10 to the 4th. And so now that is also just equal to 4. All right. You could also use the definition of a log versus an exponent to evaluate the expression. So if you have log base 3 of 243 equals x, you could just convert this into exponential form. 3 to what power equals 243? And solve it from there. All right, so x equals 5. 3 to the 3rd equals x, and so x equals 27. X to the 1/2 equals 6. Well, remember, to get rid of a rational exponent, we're just going to raise it to its reciprocal power. So we're going to square both sides, so x equals 36. When you look at the graph for these, they're going to be that reflection over the y equals x line. Remember, these are inverse operations. So our x and our y are trading places. Our domain now goes from 0 to infinity. Our range is negative infinity to positive infinity. Our function is increasing if b is greater than 1 and decreasing if it's between 0 and 1. That part doesn't change. Our x-intercept is 1, 0 instead of 0, 1. Remember, our x's and y's traded places. And the graph has a y-axis as a vertical asymptote, so x equals 0 is your vertical asymptote. The transformations, though, are going to be the same. Like if something is grouped with your x, as in here, where you have f of x equals log base 3 of x plus 3, then this is shifting to the left 3 from the original function. All right, so if this is your parent function up here, this point where it crosses at 1, 0 is going to go left 1, 2, 3 and be at 2, 0. All right. Instead of having a vertical asymptote at y equals 0, we're going to have a vertical asymptote at x equals, negative 3. And so you still have a domain, and this will go this direction here. You still have a domain, but it's this time going to be from negative 3 to infinity. Your range is the all real numbers. And then we have a vertical asymptote at x equals negative 3. All right. For the second one, log base 3 of x minus 2 is your function. I should have put f of x equals here. And so this shifts right to and down to. And so we have a vertical asymptote at 2. Okay, so notice that your domain and your vertical asymptote are connected this time instead of your range and your horizontal asymptote. Our domain is going to go from 2 to infinity. It's not flipped in any way. Okay. Let's see here. We can never take the log of 0 because you don't have anything you're raising to a power to get you 0. This one actually crosses 6, 7, 8, 9, 10, 11. Way over here is where this one crosses, and I'm getting that from just from a graph. Just graphed it. Let's see here. -2. There's a point here. So we'll go here. Like that. Your range will be all real numbers. All right, so you're going to rely on your graphing calculator. We'll talk about how to type those in because not all of yours will have a log base. But if you do, it will be go to y equals and then hit math and scroll until you see where it says log base. If not, we can get it programmed in so that it does. All right, have a good night.